Hello everyone, this is Peyton and we're going to start exam 3 by talking about the Lewis relation and how the Lewis relation can relate the heat transfer coefficient to the mass transfer coefficient, which in this case is going to be for moist air, but in any case where you can relate the heat transfer to the mass transfer coefficient, it makes it extremely nice for experimentation reasons, because in experimentation finding the heat transfer coefficient and heat diffusivities are much easier than mass transfer coefficients and diffusivities. So we're going to start by defining some of the dimensionless groups that we have already worked with. In this case, it's going to be the Sherwood and Nusselt numbers. So we're going to start with the Nusselt number, and the Nusselt number is equal to the heat transfer coefficient times some characteristic length from your problem, whether it be the diameter or the length of a tube. And then we're going to, and that is over the not the diffusivity, where's my eraser? Not the diffusion coefficient, excuse me. It should be over thermal conductivity K. And then we're going to write the Sherwood number, dimensionless group, as, again, we're going to start to see similarities between these equations because they use similar variables from them. So we're going to say that the Sherwood number, which by definition is equal to the mass transfer coefficient, or Kc, times, again, that same characteristic length over, and this time it's going to be the diffusion coefficient, dAb. So we know that this is equal to some coefficient A times the Reynolds number to the B times the Schmidt number raised to some power C. That is the definition of the Sherwood number, and we know that if you do a mass in an experimentation where you're finding mass coefficients A, B, and C, we know that they will actually be, and this is the cool part, will actually be the same coefficient A, B, C for heat transfer coefficient. So heat transfer in terms of like thermal variables and when you use those. So this relation is actually some coefficient A times Reynolds again to the B, and then instead of the Schmidt number, this is where the equations differ, as a dimensionless group Prandtl number comes into play here. So if you're looking at the relationship between B and B, C and C, A and A, they will be the same coefficients if you do the same experimentation. However, the Schmidt number is used when you're finding mass transfer coefficient and diffusion coefficient, whereas the Prandtl number is used in the case of heat transfer coefficient and thermal conductivity K. So we need to find the relationship, or an equation that relates these this heat transfer coefficient H to the mass transfer coefficient Kc. So the best way to do that would be go ahead and divide these equations out. So the Nusselt number over the Sherwood number to try and get a relation of H over Kc, or the heat transfer coefficient over the thermal, or the mass transfer coefficient Kc. So when we divide the Nusselt number by the Sherwood number, we're going to get these variables. The characteristic length is canceled out because it's the same in both equations, and you get the heat transfer coefficient times the diffusion coefficient dAb over the thermal conductivity times the mass transfer coefficient Kc. Now that we know that, when we divide, we also can say that that is equal to the Prandtl number over the Schmidt number, both raised to some power C, because the coefficients A, Reynolds number to the B, will both cancel out when you divide. So now we need to look at what's different between the Prandtl and the Schmidt numbers. So we can actually expand these right here and say that we know that the Prandtl number is the kinematics viscosity, which is mu over rho, times the thermal diffusivity alpha. And much like the Prandtl number, or much like the Nusselt number and the Sherwood number have similar qualities and variables, we will see that the Prandtl number and the Schmidt number have similarities as well. And we'll again write the thermal, or the kinematic viscosity instead of thermal diffusivity. This time it will be just the diffusion coefficient for the Sherwood number, dAb. So, and it's because of these similarities throughout is the reason we are going to help us derive that Lewis relation, or the relation between the heat transfer coefficient and the mass transfer coefficient. So when we plug these in here for the Prandtl number and the Schmidt number, we see that you get the diffusion coefficient dAb over the thermal conductivity, or not the thermal conductivity, that's K, the thermal diffusivity alpha, and that is equal to 1 over the Lewis number. So in this case, the Lewis number for moist air is and we'll derive this equation right here and expand upon the thermal diffusivity alpha is as the volumetric heat capacity, or rho Cp, times that the DAB is going to stay over, in this case, it's going to be the thermal conductivity K. So, yeah, that's a K. Okay, so we just essentially took the same equation, brought it down, and we expanded the definition of the thermal diffusivity alpha into volumetric heat capacity, OCP, over the thermal conductivity K. So now that we know these variables, we know that for moist air, we know that thermal conductivity is going to be about 0.03, density is 1.2, heat capacity is about 1,000, and then the diffusivity, DAB, is going to be around 3 times 10 to the negative third. So essentially, you don't really need to know those numbers exactly, but what you need to know for moist air is that this is going to be approximately 1, and we can set that equal to 1 over the Lewis number. So in this case, if this is going to be approximately 1 for moist air, we can say that this equation and this equation, and therefore the Nusselt number over the Sherwood number, is essentially equal to 1 for moist air. So how does this help us? Well, we pull this equation down. The heat transfer coefficient times the diffusion coefficient over the thermal conductivity times the mass transfer coefficient is approximately equal to 1. So now that we know that they're approximately 1, we set that equal to 1, and we can go about solving for the relation of H over K, or thermal or mass heat transfer coefficient over mass transfer coefficient, or H over Kc. So now that that's equal to 1, we can say that basically H over Kc, which is the heat transfer coefficient over the mass transfer coefficient, is equal to, and this is where again we're going to apply other substitution here for variables, and we're going to say that from this equation right here, we know that DAB over K is going to be equal to rho Cp is equal to 1. This equation right here is equal to 1, and therefore K over DAB is going to be equal to rho Cp. So essentially we're saying that the diffusion coefficient and the thermal conductivity have a relation now, since it's equal to 1, have a relation to the volumetric heat capacity, and that we can substitute volumetric heat capacity in for the thermal or the diffusion coefficient and the thermal conductivity here. So we know that the mass transfer coefficient Kc and the heat transfer coefficient H have a relation in which the heat transfer coefficient, H, over thermal or mass transfer coefficient Kc is equal to the volumetric heat capacity, or rho Cp, and that is actually what is called the Lewis relation. So by using the Nusselt and Sherwood numbers that have similar equations and similar variables, we were able to relate heat and mass transfer coefficients to the volumetric heat capacity, in this case for moist air, which is really cool. So now we're moving on to part 2 of the exam, which is using that Lewis relation as we found before in an energy balance to determine the relative humidity from wet and dry bulb temperatures. So what are wet and dry bulb temperatures? Well, dry bulb temperature is just the regular temperature that a thermometer gives when the bulb that's reading the temperature is dry, and true to its name, the well bulb temperature is when the bulb of a thermometer is surrounded by like a cloth and is wetted with water, and then is thrown around in the air, and then that essentially the air will evaporate the water, and the wet bulb temperature will be lower than the dry bulb temperature will be, and that's because the air will evaporate the water, and due to that difference in temperature, we can find the relative humidity from the difference in those temperatures between the wet and dry bulb temperatures. So we're going to start off by writing an energy balance for these two equations for explaining the relationship between the mass transfer and the heat transfer, because like I said, the mass transfer will be, and mass and heat transfer will be involved when the heat from the air goes into the water, evaporates it, and the mass of the water goes into the air. So we're going to start by determining the Mass transfer will be due to the difference in concentrations. In this case, it will be the difference in concentration between the surface, so the concentration of the water at the surface, essentially, and the concentration of the water in the air, or in this case, far away from the surface, as we'll label it C infinity. So the concentration at the surface minus the concentration of the water in the air. And there will need to be some kind of heat thrown in there, so we're going to have to add the heat of vaporization in order to make it an energy balance. So that is going to be equal to the heat transfer, in this case the heat transfer coefficient, or that's going to be equal to the heat flux, which is the heat transfer coefficient, and then it's going to be times the difference in temperatures, and in this case it's going to be, again, using infinity for far away from the surface, or in this case the air, it's going to be the heat transfer coefficient H times the difference in temperatures between the air and the surface. So looking at these equations, it's an energy balance right now, and here's when the Lewis relation gets put into play. So this is going to lead us to another equation. So we can see that H over Kc, if we remember the heat transfer coefficient over the mass transfer coefficient, is equal to rho Cp, or the volumetric heat capacity, which is the Lewis relation, which we found in part 1. We can divide by the mass transfer coefficient and get this equation, which is the heat of vaporization times the difference in concentration between the surface and the air is equal to the volumetric heat capacity times the difference in temperature between the air and the surface. So now that we have that equation, we can, and our goal again is to use this Lewis relation to find the energy balance, to simplify the energy balance, and then therefore find the relative humidity. And relative humidity, as I drop my eraser, relative humidity is defined in terms of pressures, so we need to start defining this equation in terms of pressures as well. So heat of vaporization is going to stay there, and we know that a concentration is simply the parcel pressure over the gas constant times temperature. So at the concentration at the surface is essentially equal to the pressure of the water at the surface, and then the concentration of the air is going to be the pressure of the water in the air, or infinity, and then over RT over that gas constant and that temperature. And now we're going to set that equal to, and in this case the density can be rewritten as the total pressure over RT, and then the heat capacity stays there, so does the difference in temperature between the air and the surface. So you may ask what temperature were you looking for here in terms of the gas constant times the temperature. In reality, it matters very little, because when we're using temperature in this case, it's going to be kelvins, and dividing by 310 is very close to, say, dividing by 305. So we're going to go ahead and say that, if I scooch over here, we're just going to go ahead and say that T is equal to an average temperature, and we'll say that average temperature is just the average temperature between the air and the water. In this case, like I said, it doesn't really matter that much. So moving on, we can see that the RTs will cancel out in these equations, and you're left with the heat of vaporization times the partial pressure of water at the surface minus the partial pressure of the water in the air is equal to the total pressure times the heat capacity times that difference in temperature between the surroundings, or the air, and the surface. So now that we have this equation, we need to remember that we're trying to solve for relative humidity, and we know that relative humidity, just going to call it RH in this case, relative humidity is equal to the pressure of the water in the air over the saturated pressure of the water at a temperature of the water, or TW. So in this case, what we were looking in this equation to solve for is the pressure of the water in the air, which in this case will be solvable from this equation here, but what we really need to find is the pressure of the water at the surface. And what we're going to find is the pressure of the water at the surface is actually equivalent to that saturated pressure of the water at a given temperature. This right here can be found using the Anton equation. So we're going to find the saturated pressure of the water at a given temperature of the water using Anton's equation, then plug it into this equation, And then from the equation, we're going to find the pressure of the water and the air, and then we'll be able to solve for RH, or relative humidity. So now we're moving on to part 3 of this exam, which is, or part 3 of the first part, which is now we're going to explain the relationship between the adiabatic saturation temperature and the wet bulb equation that we found in part 2. And we're going to be seeing that how similar these adiabatic saturation temperature equations are to the wet bulb equation that we found in part 2. So now we have an example here where we have a mass flow rate of air going through an infinitely long insulated tube at adiabatic conditions, which means there's no temperature being added to the system. So we know that there's a mass flow rate of air going into the tube at some defined temperature. We're going to say mass of air and then T in. And then we also know that it's moist air, so there's going to be a partial pressure of water, or PW, in that air. So, and then we have like I said, an infinitely long tube, in which case there's going to be liquid water, or a film of water, running over the bottom surface of this tube. And we're going to say that water at some temperature TW is consistently being added to that film, so that the temperature TW is consistent throughout the entire length of this infinitely long tube. So, like I said, there's going to be massive air in at some temperature in, and then there's going to be some temperature out, as well as there's going to be a saturation pressure of water at the defined temperature of the water at the surface of that water film. However, since the tube is infinitely long, we know that eventually enough air will evaporate that will evaporate along the edge of the tube, that the pressure of the water leaving the tube will be the same as at the surface at the end. So we can say that the pressure of the water, the saturated pressure of the water at some temperature of the water TW is going to be the same at the surface as it is coming out. So we have stuff going in and stuff going out. So we can think of this as another energy balance. So we're going to do it in terms of enthalpy. So we're going to start with enthalpy in, what's going into the system. And we're going to do enthalpy out, and we're going to set them equal to each other and find that relation there. So the enthalpy in starts with what's going in. So we have a mass flow rate of air. We have m dot air, which is how much mass is flowing in. And then we also are going to start with the sensible heat factor, which in this case would be just the heat capacity times whatever temperature is air is going in. So that would be described as the sensible heat of the sensible heat portion of the enthalpy. So, and then we also need to know how much energy is being put into the water, or what energy the heat of vaporization is playing in here. So we need to add the heat of vaporization for the water, or lambda W, heat of vaporization for the water, and that is going to be in terms of joules per kilogram. And then we need to multiply by the pressure of the water, and then that's going to be in moles, and we want kilograms, so we're going to multiply by the molecular weight to get it into kilograms, for moles into kilograms, and then we're going to divide by the gas constant times the temperature. So now that we know that, that is going to give us that is going to be joules per kilogram for the heat of vaporization, and that's going to be, this is right here is going to give us kilograms of water per kilograms of water per, and then it's going to be cubic meters of the entire system, air and water. However, we don't want air and water, we just want water. So to get rid of that cubic meters of the entire system, we're going to again multiply by RT, which is going to give us those cubic meters of everything, of the entire system, and then we're going to divide by the total pressure times the average molecular weight. And what that is going to do is that is going to stop us from getting kilograms of the entire system and just give us kilograms of water. Okay, that's right. Okay, so now that we have the sensible heat plus the factor, the heat coming, or the enthalpy for the heat of vaporization for just water, that is going to be our enthalpy in equation. So now we need to set we're going to set enthalpy in equal to enthalpy out. We got to remember that. So we are going to write our enthalpy out equation for this, and essentially it's going to be the exact same equation. It's going to be the exact same equation in many ways, except we're going to have to make a change for what the partial pressure of water is going to be in the air when it exits. So again, we have the mass flow rate of the air, and we're going to do the sensible heat factor again, which is again going to be heat capacity times, in this case it's going to be the temperature or coming out of the system, and then we're going to add again the heat of vaporization of water, and we're going to do the same thing, but this is where it changes. Instead of when it goes in, the partial pressure of water is just PW. However, when it comes out, like we said, it's got infinitely long to evaporate, so we're going to assume that, well, not assume it, just happens this way. It's got enough time to evaporate where it'll be the partial pressure of water at the surface, which is saturated at that temperature TW, is going to be the exact same pressure of water that comes out of the tube. So when it comes out, it's going to be the partial pressure or the saturated pressure of water at the given temperature TW times again molecular weight, because we want kilograms over RT. And again, that is going to give us kilograms for the entire system, and we don't want that. Oops. So we're going to multiply by RT over, again, the P total times the average molecular weight. So now that we have enthalpy in and enthalpy out, we will set enthalpy in equal to enthalpy out. And there's a couple of things that we knew right off the bat that we see will cancel out. The mass flow rate of the air will cancel out. So let's go ahead and do that when we rewrite them. Heat capacity times the temperature in, which is the sensible heat coming in. And then we're going to keep everything else. So heat of vaporization for the water times partial pressure of the water going in, molecular weight of the water over RT times RT over, again, the temperature is not going to matter because it's going to eventually cancel out, over the total pressure times the average molecular weight. And that is going to be equal to what's coming out. In this case, it's going to be equal to this equation right here. And again, we're getting rid of the mass flow rate. So the sensible heat is heat capacity times temperature out for it going out. And then we're going to add the heat of vaporization for the water times the saturated pressure of water at TW times the molecular weight. I might run out of room here, over RT. Oh, don't want to bump my camera. Times RT, we'll go down to one more row, times RT over the total pressure times the average molecular weight. And again, that's just getting us kilograms of water, and because this right here is just giving us kilograms of the entire system. So we multiply by that meters cubed over kilograms of water to get multiply that by the kilograms of entire system over meters cubed. So now that they're equal to each other, we can see a lot of common similarities between each sides, and what we're going to do is we're going to subtract the sensible heat in from this side, put it onto this side, and then likewise subtract this term and put it on this side. So what we're going to do is eventually multiply the heat of vaporization of the water, and then we're also going to pull out molecular weight of water, or molecular weight, and then we're going to say that's multiplied by the partial pressure of water going in minus the partial pressure of water coming out, which is the saturated pressure at TW, is equal to CP, or the heat capacity, times temperature out minus temperature in. So now that we have this equation, which is, we'll say this is the part 3 equation, we can feel like I'm missing something here. I'm missing, yeah, the P total pressure and molecular weight average should still be on this side. There we go. Okay. So now that we have this equation from part 3, we can go back to our equation from part 2, and we're going to add the molecular weights in there because heat of vaporization can be in terms of joules per kilogram as well as joules per mole. So in the first part, we were assuming it was joules per kilogram or joules per mole already, in which case we're not going to do that this time. We're just going to go ahead and say that equation 2 is the heat of vaporization of water again, and then times the molecular weight, and then this is going to be P. I'm changing the terminology just a little bit because we're using different terminology here. So instead of PW at infinity, it's going to be PW, and then PWS is going to be the partial pressure of water in the air is going to be the partial pressure of water, and then the partial pressure of water at the surface is going to be the saturated partial pressure of water at the given temperature TW, and then T infinity is going to be that T in, and then T out is going to be the temperature. Is going to be TS. So we are going to change them a little bit, but this is going to be the saturated. That's some given temperature PW minus partial pressure of water is equal to heat capacity times T in minus T out, because we're changing how we're labeling them now, times the pressure total times the average molecular weight. So we can see that these equations, after redefining what we're calling our variables here, are exactly identical, except for the fact that we are subtracting the saturated temperature from the partial pressure of water in the second equation, whereas we're doing opposite in this one. But since the temperatures and the partial pressures are being flipped, and we can essentially reverse the negative sign, and we can rewrite equation 2 as exactly equation 3. So that's how the enthalpy energy balance equations from the adiabatic saturation temperature relate to the wet bulb equation that we found in part 2.